Right now, the Virtual Telescope project is observing interstellar comet 3I Atlas exhibiting an ion tail that contradicts every prediction about how quickly an interstellar visitor should respond to solar heating, leaving scientists unsettled. On November 10th, robotic telescopes in Manciano, Italy recorded something that should not be happening at this stage of the comet's approach. The ion tail, a luminous stream of electrically charged particles stretching 0.7 degrees across the sky, roughly equivalent to the width of 1.5 full moons, has grown dramatically longer and more structured in a matter of days. This is the third confirmed interstellar object ever detected entering our solar system, and it is behaving in ways that challenge fundamental assumptions about the composition and thermal response of objects born in alien star systems. Gianluca Masi, founder of the Virtual Telescope project and the astronomer who captured the image using 18 separate 120-second exposures, made a careful observation. The ion tail is showing better and better development. That phrase, delivered with scientific restraint, masks a deeper puzzle. Ion tails form when ultraviolet radiation from the sun strips electrons from gas molecules venting from a comet's surface, creating charged ions that are swept into space by the solar wind, a relentless stream of particles flowing outward at speeds exceeding 1 million miles per hour. The tail always points directly away from the sun, regardless of the comet's direction of travel. What matters here is the intensity and the timing. The comet should not be releasing this much gas this quickly. The models do not account for it. Here's where it gets interesting. Early spectroscopic data suggests that 3I Atlas may contain a high fraction of carbon dioxide ice, a volatile substance that sublimates, transitions directly from solid to gas, at temperatures far lower than water ice. Carbon dioxide begins to vent vigorously when a comet reaches a distance of roughly 3 astronomical units from the Sun, approximately 280 million miles, well beyond the orbit of Mars. If this comet is rich in carbon dioxide, and if it formed in a planetary system colder and chemically different from our own, then its thermal behavior will not match the profiles built from studying comets native to our solar neighborhood. The problem is that no one expected an interstellar visitor to carry such a high carbon dioxide fraction. The assumption, based on limited data from 1I Oumuamua and 2I Borisov, was that interstellar comets would resemble the objects in our Oort cloud, dominated by water ice, with modest amounts of carbon monoxide and methane. 3I Atlas is rewriting that assumption in real time. Stop and consider that. The image was captured despite severe observational challenges. The comet was only 14 degrees above the eastern horizon, a position that forces light to pass through a thick layer of Earth's atmosphere, scattering and distorting the signal. A 61% illuminated moon was blazing just 70 degrees away, flooding the sky with light pollution. Under these conditions, most cometary features would be washed out, reduced to faint smudges barely distinguishable from background noise. Yet the ion tail of 3I Atlas remained sharply defined, luminous, and structured. That tells researchers something critical. The rate of gas release is not marginal. It is intense. The comet is venting material at a level that overwhelms the interference, and and that level is higher than theoretical models predicted for an object of this size at this distance from the Sun. Now about the data. The 0.7 degree tail spans approximately 700,000 miles at the comet's current distance. That is nearly 3 times the distance between the Earth and the Moon. The fact that this structure is visible and coherent indicates a sustained directional outflow of ionized gas, likely dominated by carbon dioxide, but potentially including carbon monoxide, cyanide radicals, and other volatiles that sublimate readily. The image also reveals a faint anti-tail, a perspective effect caused by dust grains trailing along the comet's orbital path. When viewed from certain angles, this dust can appear to extend in the opposite direction of the ion tail, creating the illusion of a secondary tail pointing toward the Sun. The presence of an anti-tail confirms that 3I Atlas is not only releasing gas but also shedding dust, another sign of escalating surface activity. Here's the problem. Interstellar objects spend billions of years drifting through the frozen void between stars, exposed to cosmic radiation, micrometeorite impacts, and temperatures just a few degrees above absolute zero. That environment should harden the surface, creating an insulating crust that suppresses gas release when the object first enters the warmth of a new star. Oumuamua, the first interstellar visitor detected in 2017, showed no detectable cometary activity whatsoever. It was inert, tumbling, and puzzling. 2I Borisov, discovered in 2019, did exhibit a tail, but its behavior was consistent with comets from our own solar system, suggesting that whatever crust had formed was thin or patchy. 3I Atlas is different. Its tail is growing faster than expected, which implies either that its surface crust is unusually thin or that its interior is unusually rich in volatiles, or both. The implications ripple outward. If the crust is thin, why? If the interior is volatile-rich, what does that say about the temperature and chemistry of the star system where it formed? Think about what that means. Every comet carries a chemical fingerprint of its birthplace. The ratio of different isotopes, the abundance of carbon dioxide versus water ice, the presence of organic molecules. These details encode information about the temperature, radiation environment, and elemental composition of the disk of gas and dust from which the comet condensed billions of years ago. If 3I Atlas is carbon dioxide rich, it likely formed in a region of its native protoplanetary disk that was colder than the equivalent region in our early solar system. Carbon dioxide ice condenses at temperatures around -125 degrees Fahrenheit, while wine requires temperatures closer to -200 degrees Fahrenheit to dominate. A comet with a high carbon dioxide fraction suggests formation beyond the snowline of a star dimmer or cooler than our Sun, or in a disk with unusual chemical abundances. Either scenario provides a window into the diversity of planetary systems in the galaxy, a diversity that remains poorly understood because direct imaging and spectroscopy of distant exoplanets captures only the largest, hottest worlds. Small, icy bodies like 3I Atlas are invisible at interstellar distances. The only way to study them is to wait for them to arrive. Researchers at the European Southern Observatory, the Harvard-Smithsonian Center for Astrophysics, and the Jet Propulsion Laboratory are now coordinating observations across multiple wavelengths, attempting to capture spectra that will reveal the precise composition of the gas and dust streaming from the nucleus. Dr. Michelle Bannister, a planetary astronomer at the University of Canterbury in New Zealand, who has studied both 2I Borisov and trans-Neptunian objects, offered a measured assessment. What we're seeing is a comet that's responding to solar radiation in a way that suggests either a different volatile mix or a different internal structure than we've modeled. It's too early to say which, but the tail growth rate is definitely on the high end of what we'd expect. That's the voice of caution, the refusal to overstate conclusions before the data are complete. But embedded in that statement is an acknowledgement that something unexpected is happening. Dr. Davide Farnocchia, a navigation engineer at JPL who specializes in the orbital dynamics of small bodies, pointed out another wrinkle. If the outgassing is asymmetric, it will exert a non-gravitational force on the nucleus, altering the trajectory in ways that are difficult to predict without continuous astrometric measurements. We need to track this object as precisely as possible to refine the orbit and determine whether it will make future close approaches to any planet. The concern is practical. Non-gravitational forces, caused by jets of gas venting preferentially from one side of a spinning nucleus, can nudge a comet's path by thousands of miles over the course of weeks. For an interstellar object on a hyperbolic trajectory, already moving faster than the escape velocity of the solar system, even small perturbations can shift the exit angle, changing which stars the object will pass near in the distant future. That might seem abstract, but it has consequences. If 3I Atlas is venting asymmetrically, the orbit we calculate today may not match the orbit 3 months from now. That uncertainty complicates every observation, every spectroscopic campaign, every attempt to predict when the comet will be optimally positioned for study. Here's where things get strange. The comet's coma, the diffuse cloud of gas and dust surrounding the solid nucleus, appears unusually compact in the November 10th image. A compact coma typically indicates that gas is escaping rapidly, without lingering long enough to form a broad, extended envelope. That's consistent with high-velocity jets, the kind produced when subsurface ice suddenly breaks through a thin crust, releasing pressurized gas in concentrated bursts. If that's happening, then the nucleus is not simply melting uniformly as it approaches the sun. It is fracturing, cracking, venting from discrete active regions. That behavior has been observed in short-period comets like 67P Churyumov-Gerasimenko, which the European Space Agency's Rosetta mission studied in exhaustive detail from 2014 to 2016. Rosetta revealed a nucleus covered in pits, scarps, and cliffs, with jets erupting from localized fissures as sunlight heated the surface unevenly. But 67P had been orbiting the sun for thousands of years, its surface battered and reshaped by repeated passages. 3I Atlas is entering the inner solar system for the first time. Its surface should be pristine, untouched by prior solar heating. If it's already exhibiting jet-driven outgassing, that suggests the crust was never thick, or that the interior volatiles are under pressure, or that the thermal conductivity of the surface is higher than expected, allowing heat to penetrate rapidly. None of those possibilities aligns cleanly with the standard model of interstellar comet evolution. Read between the lines. The scientific community is watching 3I Atlas with a mixture of excitement and unease. Excitement because every data point refines our understanding of how planetary systems beyond our own produce, eject, and distribute icy bodies through the galaxy. Unease because the behavior of this object does not fit neatly into the framework built from 1I Oumuamua and 2I Borisov. The first interstellar visitor was silent, the second was familiar, and the third is somewhere in between, active but anomalous. That sequence suggests a troubling conclusion. The population of interstellar objects is more diverse than anyone anticipated, and the handful of examples detected so far may not be representative. If carbon dioxide-rich comets like 3I Atlas are common among interstellar visitors, it implies that many planetary systems produce icy bodies in colder, more carbon-rich environments than our own. If they are rare, then 3I Atlas is an outlier, and the question becomes why we detected it instead of something more typical. Statistical arguments cut both ways. A small sample can reveal trends, or it can mislead. Right now, the sample size is 3, and the conclusions are fragile. The mechanics of ion tail formation add another layer of complexity. When ultraviolet photons strike a molecule of carbon dioxide, they can ionize it by knocking loose an electron, creating a positively charged ion. The solar wind, composed mostly of protons and electrons, streaming outward from the sun's corona at speeds approaching 400 kilometers per second, interacts with these ions through electromagnetic forces. The ions are accelerated along magnetic field lines embedded in the solar wind, dragged away from the nucleus at velocities far higher than the comet's orbital speed. The result is a tail that can extend for millions of miles, constantly replenished as fresh gas vents from the surface. The structure of the tail depends on the density and composition of the outflowing gas, the strength and orientation of the interplanetary magnetic field, and the intensity of solar radiation. A well-defined, sharply bounded tail like the one visible in the November 10th image suggests a steady, high-density outflow, which in turn requires a large reservoir of near-surface volatiles. That reservoir has to come from somewhere. If the nucleus is small, say less than a mile in diameter, then the volatile content per unit volume must be exceptionally high. If the nucleus is larger, then the surface area available for outgassing increases, but so does the mass, and the thermal response slows. Estimates of the nucleus size are still uncertain. Pending high-resolution imaging from observatories like the Hubble Space Telescope or ground-based facilities equipped with adaptive optics. But preliminary calculations based on brightness and assumptions about surface reflectivity suggest a diameter in the range of 1 to 3 kilometers. That's similar to 2I Borisov, which was about 1.4 kilometers across. The difference is that 2I Borisov's tail growth was more gradual, more predictable. 3I Atlas is accelerating. Consider the implications for planetary system architecture. Comets are not born in isolation. They form in the outer regions of protoplanetary disks, where temperatures are low enough for volatiles to freeze, and where gravitational interactions with forming planets can scatter them into distant orbits or eject them into interstellar space. The composition of a comet reflects the local conditions in the disk at the time and place it formed. A carbon dioxide-rich comet implies a region where carbon monoxide and carbon dioxide ices were abundant relative to water, which in turn suggests either a colder temperature or a different elemental composition in the gas from which the disk condensed. Stars with lower metallicity, meaning fewer heavy elements like oxygen and nitrogen relative to hydrogen and helium, might produce disks with different ice chemistries. Stars that formed in denser regions of the galaxy, where supernova remnants and stellar winds enriched the interstellar medium with carbon and other elements, might also produce unusual comet compositions. 3I Atlas could be a messenger from such a system, carrying information encoded in the ratios of isotopes and molecules that no telescope has yet been able to resolve at interstellar distances. The timeline of observations is critical. The comet was first detected by the Atlas Survey, a network of telescopes in Hawaii and Chile designed to scan the sky for near-Earth asteroids and other transient objects. The discovery was announced in July 2020 when 3I Atlas was still beyond the orbit of Mars, faint and unremarkable. Initial orbit calculations revealed a hyperbolic trajectory with an eccentricity greater than 1. The signature of an object not bound to the Sun, arriving from interstellar space. Confirmation required weeks of follow-up observations from observatories around the world, tracking the comet's motion against the background stars to refine the orbital elements. By late September, the hyperbolic nature of the orbit was beyond doubt, and 3I Atlas was officially designated the third interstellar object. Early images showed a faint coma but little tail structure. By mid-October, as the comet crossed inside the orbit of Mars, the tail began to emerge. The November 10th image represents the most dramatic development yet, captured at a time when the comet is still more than 100 million miles from the Sun, roughly the distance of Earth's orbit. Perihelion, the point of closest approach to the Sun, is not expected until late December 2025 when 3I Atlas will pass within 70 million miles of the Sun, just inside the orbit of Venus. If the current trend continues, the tail will grow even longer and more intense, potentially becoming visible to the naked eye from dark sky locations in the southern hemisphere. That would make 3I Atlas the first interstellar comet bright enough for amateur astronomers to observe without telescopes. A milestone that would galvanize public interest and trigger a surge in observations. But visibility is not the same as understanding. The brightness of the tail depends on the rate of gas release, the ionization efficiency, and the scattering properties of dust, all of which are variable and difficult to model without detailed compositional data. Spectroscopy holds the key. By dispersing the light from the coma and tail into its component wavelengths, astronomers can identify the specific molecules present and measure their abundances. Carbon dioxide produces characteristic emission lines in the ultraviolet and infrared. Water vapor, carbon monoxide, methane, ammonia, hydrogen cyanide, and formaldehyde each have unique spectral signatures. The ratios of these molecules provide clues to the temperature and pressure conditions under which the comet's ice is formed. Isotopic ratios, such as the ratio of deuterium to hydrogen in water molecules, reveal whether the comet's ice came from the same reservoir that supplied Earth's oceans or from a chemically distinct source. Measuring these ratios requires large telescopes and sensitive spectrographs. Instruments like the Very Large Telescope in Chile, the Keck Observatory in Hawaii, or the James Webb Space Telescope in orbit. Several observing campaigns are already underway, but data reduction and analysis take time. The first detailed spectroscopic results are not expected until late November or early December, by which point the comet's activity may have evolved further. The dust component of the tail adds another dimension. Unlike ions, which are swept away by the solar wind, dust grains are pushed by radiation pressure, the force exerted by photons striking the grain's surfaces. The effectiveness of radiation pressure depends on the size and composition of the grains. Small grains, less than a micron in diameter, are pushed more efficiently and form tails that closely follow the ion tail. Larger grains, tens of microns or more, are pushed less efficiently and lag behind, creating the curved, yellowish-white dust tail typical of bright comets. The faint anti-tail visible in the November 10th image is composed of larger grains that have drifted along the comet's orbital path, viewed edge-on from Earth. The presence of both dust and ions indicates that the nucleus is shedding material across a range of sizes, from individual molecules to particles large enough to scatter sunlight. That diversity suggests a surface composed of mixed materials, ice interspersed with dust, organics, and possibly silicate grains. When ice sublimates, it carries dust with it, lifting particles off the surface and releasing them into space. The dust-to-gas ratio, a key parameter in comet science, determines whether the tail will be dominated by ions or by dust. Early estimates for 3I Atlas suggest a relatively low dust-to-gas ratio, meaning the tail is primarily gaseous, another hint that volatiles are abundant. The physics of non-gravitational forces cannot be ignored. Every molecule that vents from the nucleus carries momentum, and by Newton's third law, the nucleus recoils in the opposite direction. If the venting is symmetric, the recoils cancel out, and the orbit remains predictable. If the venting is asymmetric, concentrated on one side of the nucleus, or pulsing in sync with the rotation, the recoils add up, exerting a net force that changes the trajectory. This effect is well documented in comets like 1P Halley, where jet-driven perturbations have shifted the orbit by measurable amounts over centuries. For an interstellar object, the stakes are different. The hyperbolic trajectory means the comet is not returning. It will swing past the sun once and then climb back out of the solar system, eventually resuming its journey through interstellar space. But the exit trajectory depends on every force acting on the object during its brief passage, including the tiny but persistent push from outgassing. If that push is strong enough, it could alter the comet's velocity by meters per second, which over thousands of years translates to light years of displacement. Where 3I Atlas ends up, which stars it might pass near in the distant future, depends on forces acting right now. That makes every observation urgent. Competing explanations for the comet's behavior are beginning to crystallize. One hypothesis centers on composition. If 3I Atlas formed in a planetary system where carbon dioxide ice was more abundant than water ice, then its thermal response would naturally differ from solar system comets. Carbon dioxide sublimates at higher temperatures than water, meaning the comet would start venting earlier and more vigorously as it approaches the Sun. This explanation is elegant and consistent with the spectroscopic hints of high carbon dioxide content. The challenge is that it requires the comet to have formed in a region of its natal disk that was significantly colder or chemically distinct from the regions where our own comets formed. That is plausible, but raises questions about the frequency of such systems. Are carbon dioxide-rich disks common? If so, why haven't we detected more interstellar comets with similar behavior? If not, why was 3I Atlas ejected into interstellar space while other, more typical comets remained bound to their host stars? A second hypothesis focuses on structure. Perhaps the nucleus is unusually porous, riddled with voids and fractures that allow heat to penetrate rapidly, vaporizing subsurface ice more efficiently than in a solid, monolithic body. Porous comets have been observed in our solar system, most notably 9P Tempel 1, which NASA's Deep Impact mission struck with a copper impactor in 2005, revealing a fluffy, low-density interior. If 3I Atlas is similarly porous, then even modest solar heating could trigger vigorous outgassing by creating a network of pathways through which gas can escape. This explanation accounts for the rapid tail growth without requiring exotic chemistry, but it introduces a new puzzle. Why would an interstellar object, bombarded by cosmic rays and micrometeoroids for billions of years, retain a porous structure? Conventional wisdom holds that such bombardment would compact the surface, creating a denser, more resistant crust, unless the interior remained insulated, shielded by overlying layers, allowing primordial porosity to survive. A third hypothesis invokes thin crust. If the crust that formed during the comet's long journey through interstellar space is thinner or more fragile than expected, then solar heating could break through quickly, exposing fresh ice to sunlight and triggering runaway sublimation. This scenario explains the timing, the rapidity of the onset of activity, and the intensity of the outgassing. It also implies that the mechanisms that build and maintain surface crusts on interstellar objects are not well understood. Cosmic ray bombardment, micrometeorite impacts, and the slow alteration of surface chemistry by radiation all contribute to crust formation. But the relative importance of each process and the resulting thickness and strength of the crust remain uncertain. If 3I Atlas has a thin crust, it could mean that the object spent less time in interstellar space than assumed, or that it traveled through a region of space richer with lower radiation exposure, or that the crust simply fractured under thermal stress as the comet heated. Each possibility opens new lines of inquiry. None of these explanations is fully satisfying. Each fits some of the data but leaves gaps. That tension, the inability to settle on a single coherent narrative, drives the scientific process forward, compelling researchers to gather more data, refine models, and test predictions. The next round of observations will focus on spectroscopy, astrometry, and photometry. Spectroscopy to determine the exact molecular composition and isotopic ratios. Astrometry to track the comet's position with subarc-second precision, detecting any deviations from a purely gravitational trajectory. Photometry to measure brightness changes over time, revealing the rotation period and identifying active regions on the surface. The European Space Agency's Rosetta team has proposed using archived data and techniques developed during the 67P mission to model 3I Atlas's nucleus, estimating its size, shape, and rotation from ground-based observations. The James Webb Space Telescope has dedicated observing time scheduled for early December, when the comet will be bright enough and positioned favorably for infrared spectroscopy. JWST's sensitivity in the infrared is unmatched, capable of detecting carbon dioxide, carbon monoxide, methane, and water vapor with high precision, even in the faint coma of a distant comet. Those observations will either confirm the carbon dioxide-rich hypothesis or force a rethinking. Meanwhile, theoretical models are being updated. Computational simulations of interstellar comet formation, transport, and evolution are incorporating the new data from 3I Atlas, exploring parameter space to identify conditions that could produce the observed behavior. Researchers at the University of Leiden in the Netherlands, the Max Planck Institute for Solar System Research in Germany, and the University of California, Los Angeles, are running simulations that vary the initial composition, porosity, and thermal properties of model nuclei, calculating the expected outgassing rates as a function of distance from the Sun. Early results suggest that a combination of high carbon dioxide content and moderate porosity can reproduce the tail growth rate, but only if the surface crust is thin, less than a few centimeters thick. That's thinner than the crusts predicted for objects that spent billions of years in interstellar space, which poses a problem. Either the models of crust formation are wrong, or 3I Atlas is not as old as assumed, or some process stripped away the crust during the comet's journey. Each scenario has implications that ripple through the broader field of planetary science. The question of origin remains unresolved. Where did 3I Atlas come from? Tracing the orbit backward, extrapolating its trajectory into the past, reveals that the comet is not approaching from any particular direction in the sky. Its incoming velocity and angle suggest it has been wandering through the galaxy for millions, possibly tens of millions of years, long enough for any original trajectory linking it to a specific star to be erased by gravitational perturbations from passing stellar systems. The nearest stars to the Sun, Proxima Centauri and Alpha Centauri, are ruled out. The comet's trajectory does not point back to them. More distant stars, within a few dozen light-years, are statistically more likely candidates. But without precise astrometry spanning decades or centuries, it is impossible to identify a single source. The comet could have been ejected from a planetary system around any of thousands of stars, or it could have formed in a molecular cloud and been set adrift before a star even formed. The lack of a clear origin story frustrates attempts to place 3I Atlas in context, to connect it to known stellar populations or regions of star formation. It is an object without a past, defined only by what it does now, in the brief moment it spends passing through our neighborhood. The broader implications extend beyond 3I Atlas itself. Every interstellar object that enters the solar system is a probe, a natural spacecraft that brings information from distant corners of the galaxy. The composition, structure, and behavior of these objects encode details about the diversity of planetary systems, the efficiency of planet formation and ejection processes, and the chemical evolution of the galaxy over billions of years. The current detection rate, roughly one interstellar object every few years, is almost certainly biased toward the brightest, most active examples. Fainter, inactive objects pass through unnoticed. Improving the detection rate requires better surveys, telescopes that scan larger areas of the sky more frequently with greater sensitivity. The Vera C. Rubin Observatory, scheduled to begin full operations in late 2025, will transform the field. Its 8.4-meter mirror and 3.2 gigapixel camera will image the entire visible sky every few nights, detecting faint, fast-moving objects that current surveys miss. Estimates suggest Rubin could discover dozens of interstellar objects per year, providing a statistically robust sample for the first time. With that sample, patterns will emerge, correlations between composition and size, between activity level and origin, between structure and thermal response. 3I Atlas is a preview, a single data point in a distribution that will soon be mapped in detail. But previews can mislead. If 3I Atlas is an outlier, unusually active or compositionally extreme, then extrapolating from its behavior to the broader population would be a mistake. If it is typical, then the interstellar comet population is more volatile-rich and thermally responsive than models based on solar system comets predict, which has consequences for understanding how planetary systems lose material to interstellar space. The balance between formation and ejection, between the comets that remain bound to their host stars and those that escape, depends on the architecture of the planetary system, the masses and orbits of the planets, and the density of the protoplanetary disk. Systems with massive outer planets like Jupiter are efficient ejectors, flinging comets into interstellar space through gravitational slingshots. Systems without such planets retain their comets, or lose them more slowly through interactions with passing stars. The population of interstellar comets reflects the demographics of planetary systems across the galaxy, a demographic profile that is only now beginning to come into focus through exoplanet surveys and direct imaging campaigns. Think about what that means for the search for life. Comets deliver water, organic molecules, and other volatiles to planets. In our solar system, the bombardment of Earth by comets and asteroids during the late heavy bombardment, roughly 4 billion years ago, may have supplied much of the water now in the oceans and seeded the planet with the chemical building blocks for life. If interstellar comets are common, then the exchange of material between planetary systems is not negligible. A comet ejected from one star system could, over millions of years, wander into another, impacting a planet and depositing volatiles and organics from an alien world. The probability of any single comet making such a journey and striking a habitable planet is vanishingly small. But over the lifetime of the galaxy, with billions of stars and trillions of comets, the cumulative effect might be significant. Panspermia, the hypothesis that life or its precursors spread between star systems via comets, asteroids, or ejected planetary material, remains speculative, but every interstellar object detected adds a data point, a small increment to the plausibility of such mechanisms. If 3I Atlas is rich in organics, which spectroscopy will eventually reveal, it strengthens the case that the building blocks of life are not confined to individual planetary systems, but circulate through the galaxy, hitchhiking on objects like this. The rotation of the nucleus is another variable awaiting measurement. Comets typically rotate with periods ranging from hours to days, the result of torques accumulated during formation and subsequent gravitational interactions. If outgassing is concentrated in jets, those jets can spin up or spin down the nucleus, changing the rotation rate over time. Measuring the rotation period of 3I Atlas requires photometric observations spread over multiple nights, tracking brightness variations as different areas of the surface come into and out of sunlight. Preliminary light curves, incomplete and noisy, suggest a rotation period somewhere between 10 and 20 hours, but the data are not yet conclusive. A well-determined rotation period would allow researchers to model the orientation of the spin axis and the locations of active regions, linking the observed outgassing to specific features on the surface. That kind of spatial resolution is not achievable with current ground-based telescopes, which see 3I Atlas as a point of light, but modeling can fill in the gaps, using physics and statistics to infer structure from brightness alone. The anti-tail, faint but persistent in the November 10th image, offers clues about the dust. Anti-tails form when a comet's orbit carries it through the plane of its own dust trail, allowing the trail to be viewed edge-on from Earth. The dust grains, released weeks or months earlier, drift slowly under the influence of radiation pressure and gravity, forming a thin sheet that extends along the orbital path. When Earth's line of sight intersects that sheet at a shallow angle, the dust appears as a narrow spike pointing toward the Sun, opposite the ion tail. The visibility of an anti-tail depends on geometry, on the alignment of the comet's orbit, Earth's orbit, and the distribution of dust. The fact that 3I Atlas is displaying an anti-tail now indicates that the comet has been shedding dust steadily for at least several weeks, long enough for the grains to spread along the orbit. That steady shedding is consistent with continuous outgassing, as opposed to sporadic bursts. It also implies that the dust production rate, though lower than the gas production rate, is not negligible. Dust complicates the dynamics, adding mass loss that must be accounted for when calculating the comet's trajectory and predicting future positions. Here's where things get strange again. If the tail growth continues at the current rate, 3I Atlas will develop one of the longest ion tails ever recorded by the time it reaches perihelion. The record holder, comet Hyakutake in 1996, produced a tail extending more than 350 million miles, a length so vast it stretched beyond the orbit of Mars. Hyakutake was a long-period comet from the Oort cloud, making its first close approach to the Sun in thousands of years, venting volatiles that had been frozen since the solar system's formation. 3I Atlas is coming from even farther, from interstellar space. And if its volatile content is as high as the data suggest, there is no reason it couldn't match or exceed Hyakutake's tail length. The spectacle would be extraordinary, a glowing streamer spanning a significant fraction of the night sky, visible to anyone with clear skies and a dark observing sight. But spectacle is secondary. What matters is what the tail reveals about the comet's interior, about the conditions in the planetary system where it formed, about the processes that shaped it during its long exile in the space between stars. Read between the lines again. The scientific literature on interstellar objects is sparse, dominated by just two prior examples. One-Eye Oumuamua defied easy classification, appearing asteroidal but accelerating in a way that suggested outgassing, though no coma or tail was detected. Explanations range from exotic, invoking hydrogen icebergs or alien spacecraft, to mundane, attributing the acceleration to asymmetric venting of nitrogen ice or water vapor below the detection threshold of available instruments. The debate remains unresolved, a reminder that single objects, observed briefly with limited resources, can generate more questions than answers. 2I Borisov was less controversial, a clear comet with a well-developed coma and tail, composition similar to solar system comets, behavior unremarkable. It came, it was observed, it left, adding a single well-behaved data point to the ledger. 3I Atlas is the wild card, active but anomalous, familiar in form but strange in degree. It forces a recalibration, a recognition that the interstellar object population is not monolithic, that diversity is the rule rather than the exception. The technological challenge of studying 3I Atlas cannot be overstated. The comet is faint, fast-moving, and embedded in a sky crowded with stars, galaxies, and other transient phenomena. Extracting its signal from the noise requires large telescopes, sensitive detectors, sophisticated data processing, and coordination across multiple observatories and time zones. The Virtual Telescope Project's November 10th image is a triumph of remote, robotic observing, demonstrating that meaningful science can be done even under adverse conditions: low elevation, bright moon, limited exposure time. But that image is just one snapshot, a single moment in a dynamic process. To understand 3I Atlas fully requires continuous monitoring, tracking changes on timescales of hours to weeks, correlating brightening events with spectroscopic changes, measuring the tail's length and structure as a function of distance from the Sun. That level of coverage demands resources, telescope time, and human effort, all of which are finite and must be allocated carefully. The comet is competing for attention with supernovae, gamma-ray bursts, exoplanet transits, and 1,000 other celestial phenomena, each with its own scientific importance. The allocation of resources reflects priorities, and right now 3I Atlas is a priority, but that could change if another, brighter interstellar object appears, or if the comet's activity plateaus and becomes predictable. The question of what comes next is practical and urgent. The James Webb Space Telescope's observing window in early December will provide the most detailed compositional data yet, but JWST's schedule is packed, and the allocated time is limited, a few hours at most. Ground-based facilities will continue to track the comet through perihelion and beyond. But as 3I Atlas moves farther south in the sky, it will become inaccessible to Northern Hemisphere observatories, shifting the burden to telescopes in Chile, Australia, and South Africa. Coordination between these facilities is essential to avoid gaps in coverage. The Hubble Space Telescope, though aging, remains capable of high-resolution imaging and could resolve the nucleus directly if the comet brightens sufficiently. Proposals have been submitted for Hubble time in late December and early January, when 3I Atlas will be near its brightest. Approval is not guaranteed, but the potential scientific return is high enough to justify the request. Amateur astronomers, equipped with increasingly sophisticated cameras and telescopes, are also contributing. Networks of amateur observers across Europe, North America, and Asia are imaging 3I Atlas nightly, measuring its brightness, tracking the tail's evolution, and reporting their findings to professional researchers through platforms like the Central Bureau for Astronomical Telegrams. The democratization of astronomy, the ability of non-professionals to make meaningful contributions, has expanded the observational capacity of the field, providing data that would be impossible to gather with professional telescopes alone. The collaboration between amateurs and professionals, mediated by open data sharing and common standards, is one of the success stories of 21st century astronomy, and 3I Atlas is benefiting from it. But data are only as good as the models used to interpret them. Theoretical work is racing to keep pace with observations, updating models of cometary outgassing, radiation pressure, and non-gravitational forces to account for the peculiarities of interstellar objects. The challenge is that interstellar comets do not have the luxury of multiple orbits to reveal their behavior. Solar system comets can be studied over many passages, their activity tracked and modeled, their orbits refined with each return. Interstellar comets pass once and vanish, leaving researchers with a single snapshot, a brief window of opportunity to gather data before the object fades and becomes unobservable. That urgency intensifies the pressure, compressing years of study into months, forcing decisions about where to point telescopes, which measurements to prioritize, which questions to pursue. Every choice involves trade-offs. The risk that a critical observation will be missed, that a unique opportunity will be squandered. The cultural impact of interstellar objects extends beyond science. They are emissaries from the void, tangible evidence that the space between stars is not empty, but populated with debris from planetary systems near and far. Each detection is a reminder that the galaxy is dynamic, that matter circulates on timescales far longer than human history, that the solar system is not isolated, but embedded in a larger ecosystem. For the public, interstellar comets like 3I Atlas are a bridge between the familiar and the alien, objects that can be seen and photographed, yet come from places unreachable by any current or foreseeable technology. They inspire wonder, but also humility, a recognition of how little we know about the universe beyond our immediate neighborhood. The possibility that 3I Atlas could become visible to the naked eye is exciting and unusual. Naked eye comets appear maybe once a decade, and if this one brightens enough, it would be the first interstellar comet ever seen without a telescope. But comets are unpredictable. 3I Atlas could flare brilliantly, or suddenly fragment into fading debris long before the show reaches its peak. Time is short. By late December, it will swing around the sun and begin to disappear into the dark again. Within months, only the largest telescopes will be able to find it. Every observation now is precious, data that scientists will analyze for years after the comet is gone. Early signs hint at an unusually high amount of carbon dioxide ice. If that proves true, it means this comet formed in conditions different from those of our own solar system, perhaps around a cold red dwarf star, the most common type in the galaxy. That would make 3I Atlas a rare sample from the kind of planetary systems that fill the Milky Way. Or maybe it is an outlier, a cosmic oddball we were simply lucky to detect. The world's most powerful observatories, JWST, VLT, Keck, Hubble, are now watching, joined by a global network of amateurs. Each spectrum, each image, brings us closer to understanding what this object is made of and where it came from. If its activity continues to increase, if its chemistry confirms the early clues, then 3I Atlas is not just a comet. It is a message from a distant star system, a fragment of a place we may never see, carrying secrets about the formation of other worlds. And if this visitor has such a dramatic story to tell, how many more travelers like it might be passing silently through the dark between the stars?